My dear students, let me welcome you all to a new edition of physics. In this edition, we'll revise chapter 1, electric current. What's meant by current, amperage, voltage, potential difference, and Ohm's law, and the factors affecting electric resistance. So let's get started. Electric current and Ohm's law. What's meant by electric current? Okay, it is flow of electrons. It is flow of electric charges in solid conductors. So once again, electric current is flow of electrons in solid conductor. Amperage or electric current intensity is denoted by I, and it is equal to Q over T. Q is the amount of electricity, amount of a charge. T stands for time. So current intensity is the quantity of a charge, quantity of electricity that passes in 1 second. It is the quantity of electricity that passes through a conductor in 1 second. Current intensity is measured in amperes, and we want to define ampere. What about ampere? Since I equals Q over T, so ampere must be equal to coulomb over second. So ampere is a unit of, current intensity. So it is the current intensity when the rate of flow of electricity is 1 coulomb per second. Once again, ampere is defined as the intensity of the electric current when the rate of flow of electricity is coulomb per second. Since coulomb equals ampere times second, we want to define coulomb. Coulomb is the unit of amount of charge. Okay, so it is the quantity of electricity, or it is the amount of a charge which passes any point in a circuit in 1 second when a steady current of 1 ampere is flowing. When a steady current of 1 ampere is flowing. This was the definition of coulomb. The amount of electricity, amount of a charge passes, in a circuit when a steady current of 1 ampere is flowing in the circuit, passes in 1 second. And what about the voltage, potential difference between 2 points in a circuit? Potential difference is denoted by, capital V, and it is the work required to transfer 1 coulomb between these 2 points. Potential difference is the work required to transfer 1 coulomb between 2 points. Okay, it is calculated from the expression V equals W over Q. So volt, since V equals, W over Q, so volt equals joule over coulomb. And now it's all easy for you to define volt. What's meant by volt? It is the potential difference between 2 points. So volt is the potential difference between 2 points. And what about these 2 points? Okay, when a work of 1 joule is required to transfer 1 coulomb between these 2 points. And now we've got another important definition, which is electromotive force of a cell. What is electromotive force of a cell? It is, by the way, it is denoted by EMF or V battery, subscript V and B. Okay? It is the work required to transfer unity charge through the whole circuit. I'm talking about the EMF of a cell. It is the work required to transfer one coulomb through the whole circuit. One coulomb is the unit charge. That is to say, to transfer one coulomb through the external circuit as well as the internal circuit. Another important definition of EMF of a cell is it is its terminal voltage when no current passes through the cell. So EMF of a cell is its terminal voltage when no current passes through it. And now we'll try to obtain a formula, to obtain an expression, a relation that gives electric energy. Electric energy, like any energy, is denoted by W. First of all, potential difference between 2 points is calculated from the expression W over Q. So W equals VQ. This is the first equation. Since current intensity is given from the expression Q over T, so Q equals IT. This is the second equation. From equation 1 and 2, okay, substituting for Q, we can say W equals, yes, instead of saying VQ, it will be VIT. Okay, once again, from 1 and 2, W equals VIT. We used to say it VIT. V is potential difference, I is current intensity, T is the time. Electric energy is calculated, as I said, from the expression, from the relation VIT. So talking about the units here, electric energy is measured in joules, potential in volt, intensity in ampere, time in seconds. So joule equals volt times ampere times second. And what about electric power? It is rate of conversion of electric energy, rate of consuming of electric energy or rate of producing. Okay? Power equals energy, electric energy over time. So it is electric energy, yes, consumed or produced in 1 second. And unit of power is watt, energy joule, and time is seconds. So watt equals joule over second. Since power equals energy is given by the expression VIT, okay, power equals energy over time, and of course time will be crossed out. So the expression that gives the power is the product of voltage and current. So watt equals volt times ampere. Also power can be given from the expression I squared R or V squared over R. Okay? Okay, we've got some problems here to work them out together. A student makes a resistor from a length of a wire. He then makes a second resistor using wire of the same material. Wire of the same material means same resistivity, same conductivity, of course. And what about the second resistor? Yes, it is half the diameter but twice the length. So D2 equals half D1. Diameter of the second is half that of the first. Length of the second is twice the length of the first. L2 equals 2L1. Find the ratio of the value of the second resistor to that of the first. Okay, so what's given in the problem? Second diameter equals half D1. Second length length of the second resistor is twice that of the first. It is 2L1. So R1 over R2, which is equal to L1 over L2 times D2 squared over D1 squared. Resistance is directly proportional to the length, but inversely proportional to the area. So R1 over R2 equals L1 over L2 times D2 squared over D1 squared. It is equal to half times 1 over 4. It is 1 over 8. This is the ratio between R1 and R2. So if you want to mention the ratio between R2 to R1, it will be 8 to 1. Okay, thank you very much. Another type of questions. What happens when a wire of resistance R is reshaped such that its length is doubled? Okay, the wire is reshaped and its length is doubled with respect to the new resistance of the wire. As a matter of fact, here we've got two factors affecting the resistance. When a wire is melted and reshaped such that its length is doubled, the area will be halved. Okay, this is very important to bear into your mind. So the resistance is made 4 times greater, length doubled and area halved. Okay, doubling the length will double the resistance. Okay, and when the area is halved, the resistance will be doubled again, so it will be increased 4 times. Resistance is quadrupled. It is made 4 times greater. Okay, what happens when a wire of resistance R is reshaped such that its area is doubled with respect to the new resistance of the wire? I believe you can do it right now. Area is doubled. Okay, this will affect the length. So length will be halved. Doubling the area will, yes, decrease the resistance to half its initial value. Okay, and length is halved also will decrease the resistance. Resistance will be halved once again. So it will be quartered, decreases to 1 over 4. Thank you. A wire of resistance R is reshaped such that its area is halved. Okay, what happens to the conductivity of the wire? Your attention, please. As I said before, we mentioned something very important. Conductivity and resistivity depends only on temperature and material. And both factors are unaltered, unchanged. We are changing dimensions of the wire, and this will not affect conductivity or resistivity. So conductivity remains unchanged. Conductivity is not changed. Combination of resistors. We've got 2 methods, series connection and parallel connection. We'll start with the series connection. Resistors are connected in series. Okay, this means that the current has just one path to flow. So resistance R1, R2, and R3 connected in series means they carry the same current intensity. Okay, but potential difference across R1 is V1, and across R2 is V2, and across R3 is V3. And total potential will be, yes, V1 plus V2 plus V3. Voltage is the product of current and resistance. So I, R total equals IR1 plus IR2 plus IR3. The current will be crossed out. So R total or R equivalent equals R1 plus R2 plus R3. Okay. This in the case of, yes, series connection. And in parallel connection, okay, what happens? The current, yes, what about it? It divides, it splits. So we've got 3 resistors shown in front of you connected in parallel. Okay, as I said, when they are connected in parallel, the current divides. I divides into I1, I2, and I3, and then they recombine again to form the same current intensity I. So we can say, okay, we can say I is equal to I1 plus I2 plus I3, but there is something very important here. When connecting in parallel, the voltage is the same, potential difference is the same. So voltage across R1, which is V1, equals voltage across V2, across R2, and it is equal to V3, which is across R3, and it is equal to V total. Okay, so as I said, I is equal to I1 plus I2 plus I3, applying Ohm's law. Okay, and the voltage is the same, so we can say V over R total equals V over R1 plus V over R2 plus V over R3. Voltage will be crossed out, so 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Let's solve some problems. 3 resistances, 18, 9, and 3, are connected to an electric supply of negligible internal resistance. Let me say it again. We've got 3 resistors, 18, 9, and 3, connected to an, yes, electric supply. The internal resistance of the supply is neglected. Currents of 0.1, 0.2, and 0.3 pass through them respectively. Find the EMF of the supply. First of all, we want and we need to know the way they are connected, the way the resistors are connected together. Okay, the right way to do this is to calculate the potential difference across each resistor. So potential difference across the 18 ohm resistance, it is the product of current and resistance. It is 18 times 0.1. It is 1.8 volt. This was the potential difference across the 18 ohm resistance. We'll do the same concerning the 9 ohm resistor. It is 9 times 0.2. It is 1.8, same potential. So they must be connected in parallel. Potential difference across the last resistor, the 3 ohm resistor, it is 3 times 0.3, so it is 0.9. Okay, so we can figure it out right now. 18 and 9 connected in parallel, and both connected in series to the 3 ohm resistor. Okay, and this is quite clear because the sum of the two currents, 0.1 and 0.2, will give the current passing through the 3 ohm resistor, which is 0.3. So R equivalent in this case, it is 18 times 9 over 18 plus 9 plus 3. It is 9. Okay, V battery equals I times R equivalent. It is 0.3 times 9. It is 2.7 volt. A current of 0.2 passes through a uniform wire when a potential difference of 3.6 volt is applied across it. So current and voltage are given. So it's all easy to calculate the resistance. Voltage over current. The wire is shaped into a rectangle ABCD such that length AB is twice that of BC. The wire is shaped into a rectangle, is bent into a rectangle. ABCD, but length of AB is twice that of BC. Find the equivalent resistance of the wire if an electric supply is connected across 2 points A and B, and when it is connected across A and C. Okay, so we'll try to calculate the resistance of each portion. And first of all, we need to calculate the resistance of the wire itself. Voltage over current, it is 3.6 over 0.2, it is 18 ohm. Since the wire is uniform, resistance is proportional to the length. So portion twice the length will be twice the resistance. So RAB equals 2RBC, RCB equals RDA. So we can say 2RAB plus 2RBC, they'll form the whole rectangle equals 18. So RAB plus RBC equals just 9 divided by 2. RAB plus RBC equals 9, but resistance of RAB equals, yes, 2RBC. So 2RBC plus RBC equals 9. In this way, we've managed to obtain the resistance of RBC, which is equal to 9 over 3, which is 3. Okay. And of course, resistance of AB is twice, so it is 6 ohm. Now it's all easy to calculate the equivalent resistance. When the supply is connected across AB, what happens? The current divides at A. Same current passes through 3, 6, and 3. They'll form just one resistance. 3 plus 6, 9, plus 3, 12. So 12 connected in parallel to 6, they'll give an equivalent resistance of 4. Product over sum, 12 times 6 over 12 plus 6, it is 4. And what about when they are connected across AC? It's all easy. 2 branches of equal resistance. Each branch of resistance 9. 3 plus 6. So 9 over 2, it will be 4.5. This way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.